All right, so starting a new week, starting a new section of the course, where are we? We've talked about what I maybe in this slide are calling informatics. So the management, manipulation, integration of data, and we had some emphasis on scale, and we had some emphasis on specific tools. Okay, so now we're moving into what I'll call analytics. And so we're going to talk about statistical estimation and prediction. And one of the points I want to make is that this builds on the informatics, in that the things you're going to learn you can implement using the tools before. And we already saw a piece of this where we did sort of matrix multiplication and various tools and so on. Okay. The other point, if you remember, we made early on was that 80% of what people think of as analytics really boils down to the ability to do sums and averages. And so we'll see a little bit of that in here, where maybe understanding the problem and understanding the solution is hard or easy depending on maybe your background. But as far as implementing it, it's not too bad. Okay. And then we'll move on to the visualization in a couple of weeks. All right, so to get started on this, I want to call your attention to this article in 2010 from the New Yorker, with the caveat that this is far from a research article. And in fact, a lot of what the article has to say, I'm not sure I'd recommend taking to heart. But the point, the topic that they bring up is that the title is here is "The Truth Wears Off," and what they're exploring is this notion that statistical results in the sciences seem to have gotten weaker over time. And so John Davis is a researcher at the University of Illinois who does work on antidepressants, is quoted and is discussed as talking about how a forthcoming analysis is demonstrating the efficacy of antidepressants has gone down as much as threefold in recent decades. So this is that the effectiveness as measured by clinical trials of these antidepressants has gotten a lot weaker. The article also talked about Anders Müller, who studied barn swallows and discovered that the females were more likely to mate with males that had long symmetrical feathers. And this finding sort of relied on precise measurements of the symmetry. And so this was a pretty significant discovery, but over the course of the next 5 or 6 years, the effect size, as discovered by himself and other researchers, shrank by 80%. Okay, a lot of the article talks about Jonathan Schooler in 1990, who made a discovery of an effect that he called verbal overshadowing, which was counterintuitive because it showed that people who are asked to describe a face, using English that they've seen, were actually less likely to remember it than those who had just seen the face. And so talking about the face somehow overshadowed the effect of just seeing it alone. Okay, and once again, this effect seemed to get weaker over time and became increasingly difficult to measure, but including by Jonathan Schooler himself. And in fact, he's quoted as saying this frustrated him, right? He was having trouble replicating it. Okay, and then they also bring up someone who's a little less respected, a fair amount less respected in the scientific community as an historical example, and is the person who actually coined the term the decline effect, which is brought up over and over again in the article. So in the 1930s, Joseph Ryan tested individuals with these card guessing experiments in an attempt to measure the effect of extrasensory perception, or ESP, and he's the one who actually coined that term. So he had a few students that achieved multiple streaks of very low probability, many cards in a row that they guessed right and so on. But there was a decline effect, and that the same candidates, the same participants, couldn't match their earlier performance. Okay, and so the article touches on what is essentially the correct explanation of this effect, and it also sort of brings up the possibility of a bunch of quasi, mystical, incorrect explanations of this, at least in my opinion. So I want to tell you about, I want to, in the next couple of segments, next few segments, I want to sort of explore this as a test case for statistics and statistical estimation. And I want to use this as a vehicle to introduce the fundamental concepts of statistics and also some of the somewhat more advanced concepts of statistics especially as they relate to big data. Okay, so to get started, let's talk about the background here, and then we'll come back to this specific article and explore the reasons for why the truth wears off. Okay, so this is not going to be a replacement for a introductory college statistics course. This is going to be a quick overview of the terminology and the concepts that you should be familiar with. Okay, so we're talking about statistical inference here, and so these are methods for drawing conclusions about a general population from sample data. And there's two key methods that you can use here: hypothesis tests and confidence intervals. And we're going to bring up confidence intervals again a little later on, but I'm not going to talk about them directly right now. All right. So what is hypothesis testing? Well, you're going to be comparing an experimental group to a control group. And there's always going to be a null hypothesis. And the null hypothesis is there's just no difference between these two groups, right? The one who received the treatment in question are no different than the ones who did not. The new website generates no more traffic than the old website, than the control website, than the default, and so on. Okay. So that's the null hypothesis. The alternative hypothesis is that there is an effect. There's a statistically significant difference between the two. And so here, difference is defined in terms of some test statistic. And you can, most of the examples you'll find in an introductory course, or really any course, are going to be about comparing the means, right? So the average effect in the control group was different than the average effect in the experimental group. Okay. Now, a lot of what statistics is about is actually designing the experiment to collect the data. And in a data science regime, in a big data regime, we're actually less frequently in a position to design the experiment in the first place. A lot of times we're dealing with data that we did not necessarily collect. Okay, so that's maybe one difference between classical statistics and the way I want to present this material for purposes of data science. Okay. That being said, it's important to understand that careful experimental design is really the most important thing there is in all this work, right? The analysis techniques are second fiddle to the proper collection of data. Okay, so this includes things like randomized trials, blinded and double-blinded. So, what is blinded? It means that the participants themselves don't know which group they're in, and that's pretty much non-negotiable, right? You can't tell people that they're getting a placebo drug versus the actual drug, or they'll they'll report their symptoms differently as an effect. Randomized is also would be non-negotiable, except the fact that it's difficult to achieve in practice in some cases. So randomized would mean we draw a sample through some method, and then we assign them to the groups, to the control group and the experimental group, with no process whatsoever, right? It's just purely random. Okay, so this framework, expressed in just these sort of few bullets at a high level, is unbelievably powerful, right? It's completely universal to data analysis, so it's really important to sort of internalize these points, and we'll go into some more detail on some of the other aspects that aren't included in this slide. So some examples you can dream up, that measuring the effect of a new ad placement on your website compared to the control group of the existing placement, measuring the effect of a treatment against a sugar pill or the best existing treatment, okay, and everything else you might imagine. So to summarize hypothesis testing, you can organize this terminology into this grid here, where there's two possibilities for this true state of the world. One is that the null hypothesis is true. There is no difference between the control group and the experimental group. And the other is that the null hypothesis is false, that there is an effect that you're measuring. Okay. And so then there's also two possibilities for the outcome of your statistical test. In one case, you do not reject the null hypothesis, right? You find no evidence that there's any difference between the groups. And the other is that you reject the null hypothesis. You do find evidence that there's difference between the groups. Okay. So if the null hypothesis is true, there is no difference, but you detect a difference, that's a type 1 error, and the rate at which that happens we will refer to as alpha, and that might come up at times as we have this discussion. Right. And if you make the correct decision, then the probability of that is 1 minus alpha. when the null hypothesis is true. When the null hypothesis is false and you fail to reject it, right? There is an effect and you fail to measure it. That's a type 2 error, and that's beta. And when you do reject the null hypothesis, when it's false, right? You detect an effect when there is an effect to detect. That's 1 minus beta. And this is called the power of the test, the statistical power. Okay. So in the last slide, we said that comparing two groups, the control group and the experimental group, is the name of the game. And we said that we're trying to take some test statistic and to measure the difference between those two groups. But how different is different enough to be significant? Okay, so in other words, how do we know that the difference that we saw in the experiment is not attributable to just chance? Well, the answer is we don't. But we can calculate the probability that it's attributable to chance. And that's what the p-value is. Okay, so the p-value is the following. If you were to repeat the experiment over and over and over again at the same sample size, what percentage of the time would you see results that were at least as extreme as the ones you got in this experiment? And this is all assuming the null hypothesis is true. So let me say that again. Assuming that there is no difference between the groups, right? The control group really is the same population as the experimental group, right? The treatment has no effect. If I were to do the same experiment over and over again, what percentage of the time would I see a difference in the treatment group anyway, just by chance? Okay, and that's what the p-value is. Fine. So more terminology, you need to think about two-sided versus one-sided. So two-sided is if we're measuring something in terms of the absolute value, right? So the p-value is 2 times the probability that x is greater than the absolute value of the measured value. And if the test is one-sided, it's either greater than or less than. And here the notation that we're using is mu, which is the mean, and mu sub 0, which is the mean of the population under the null hypothesis. So this screenshot is taken from a nice applet that you can find online and play with here. But here, if the null hypothesis is that the mean is 325, and we're doing a two-sided test where mu is not equal to 325, we're saying it must be something different than that, either higher or lower, right? And the sample size is 10, and the observed sample mean is 328. Then when you click the Show P button on the applet, what you get is it computes the p-value for you and shows this colored region. And so these colored regions. And so these colored regions, the area under that curve is the p-value. Okay. So that's the probability that it's at least as extreme as the measured value. Okay. And if you get, here the only change I've made is that the sample mean was 329 instead of 328, which means it's even less likely that you would see this by chance. And so the area under those curves is even smaller. And you notice the p-value changed. The p-value went from 0.0574 to 0.0114. Okay. So in order to make some sort of a decision, did this treatment work, right? Do we invest in this treatment? Do we move on to the next stage of trials? We need some sort of a threshold, some sort of a cutoff for the p-value. So what is that cutoff? Well, it's 0.05. Why? No good reason. It makes the math work out. Okay, so this is a 1 in 20 chance. If you can show it's more rare than a 1 in 20 chance, then that's deemed to be good enough. Okay, this is the subject of a lot of controversy, depending on what circles what sort of literature you're reading. And we'll talk a little bit more about this in a few segments, but that's all I'm going to say about it right now. So 0.05 is what people are looking for. All right. So now that you're armed with a little bit of basic terminology, let's go back to this first slide from this New Yorker article. And so the question that we raised was, what accounts for this truth wearing off effect? How can we explain what's going on? Okay. So one reason is publication bias. All right, so let me read you a couple of quotes from this article about publication bias. So in the last few years, several meta-analyses, and we'll talk about what a meta-analysis is in a little bit, have reappraised the efficacy and safety of antidepressants and concluded the therapeutic value of these drugs may have been significantly overestimated. Okay. Although public, and there's other examples in this article as well. Okay, so go back and review the literature and find out that things have been overstated. Why? So although publication bias has been documented in the literature for decades and origins and consequences are debated extensively, there is evidence suggesting that this bias is increasing. All right, so I haven't told you what publication bias is yet, but you may be familiar with the concept, and these are some of the effects. So a case in point in the field of biomedical research and autism spectrum disorder, which suggests that in some areas, negative results are completely absent. All right, so what does that mean? That means that you're only publishing papers that show significant positive gains, right? If we try several treatments and none of them work except for one, we try 20 treatments and only one works, how many papers do we publish? One, not 20. Okay. So how is this a problem? Okay. So do we have an explanation for this decline effect with publication bias? So how does this actually work? Well, let's make a plot where this study size is on the x-axis. And notice this is log scale, right? So this is 10, and this is 100, and this is 1,000, and so on, right? Well, study size meaning the number of patients, that are involved in the study. So the bigger the study size, the more statistical power you have, and we'll define what statistical power means precisely in a bit. But the better you are able to determine actual effects, right? And the assumption here is perhaps that, as time goes on and you see some results, you or other researchers are able to garner more money, more funding to do larger and larger studies, right? So this is maybe phase 1, phase 2, phase 3 trials of some new drug. They get bigger and bigger and bigger sets of patients as you get more momentum behind it. And this data is not real. This data is simulated. But imagine you see this kind of decline effect where the results. Okay, well, the y-axis. The y-axis is the effect size, and we'll talk about what the effect size is precisely in a little while. But this is the degree of positive outcome. Let's say, right? Let's say negative is bad and positive is good. So this is, the number of smokers you were able to convince to quit with some intervention counseling method, or the number of white blood cells increased as a result of some treatment or so on. Okay. So positive is good. Well, this decline effect, let's imagine, shows this sort of a pattern, right? Where the early studies with just 10 participants is up here, and as the study went up, it sort of got worse and worse and worse. So this is the effect that we see. How do we explain this? Well, this is directly explainable. This kind of an effect would be directly explainable just by publication bias, right? Imagine that every dot now is a test that was done by some group somewhere for this phenomenon. What you'd expect is this kind of funnel shape where the studies get more and more accurate as you get larger and larger and larger, right? And they will. With a study, this is you can't get around this, right? As the study size goes up, you do have more statistical power. You're able to better discriminate real effects from false effects, and so on. But you'll notice that the actual effect that it's regressing to here is 0.0. There is no effect. And yet, of course, you're going to get some, just due to variability, out here. And so if you only report the positive ones, you'll end up with this mysterious decline effect. Okay. Okay, so we talked about publication bias, and on the y-axis of that plot we had effect size. So what is effect size? Well, if you recall, p-value was just the probability of, in repeated experiments, getting an effect of at least that size or more extreme. Okay, and so all it tells you is yes or no whether it was significant according to some threshold. It doesn't tell you how significant it was or how important it was. Okay, and that's what effect size tries to capture. So the effect size in a situation where you're comparing the means of experimental group and control group, then the effect size is the mean of the experimental group minus the mean of the control group divided by the standard deviation. And so this tells you not just significant, but how significant. And this measure is used prolifically in meta-analysis to combine results from multiple studies. And it's useful to help standardize across studies with different parameters, different sample sizes in particular, for example. Okay. And so in general, you got to be careful with this because averaging results from different experiments can produce nonsense if you sort of violate the assumptions under which the experiments were conducted. But, it can be done. Okay. And so another caveat here is that there's other definitions of effect size exist. There's odds ratio and correlation coefficient, but we're just going to talk about this one. Okay. And so there's an argument here that the effect size should always be reported along with the p-value, even though this is very rarely done. And that argument is delivered by Robert Coe in this paper presented at the annual conference of the British Educational Research Association in 2002 that's cited here at the bottom of the slide. Okay. So a little more precisely, the effect size is the standardized mean difference where the group 1, the mean of group 1 minus the group 2 divided by, we said, the standard deviation. And here I'm writing this as the standard deviation subpooled. Okay, and there's lots of ways to compute a value for this notion of pooled. One simple way is just to take the standard deviation of the control group. And, one by one argument here, hey, the variation is supposed to be the same because the sample, the two groups are drawn from the same population. Okay. Another way is to compute the actual pooled standard deviation, which is an expression that looks like this. And so we're not going to go into much more detail than that. But just to point out that the overall notion is pretty simple and that it's not unreasonable to use a straightforward definition of the standard deviation. Okay. So what's a big effect size? Well, because it is standardized, you can actually reason about what might be big and what might be small. So this is, again, one of these cases where it's sort of made up on the fly, but you can, one heuristic by Jacob Cohen is a small effect size is 0.2, a medium effect size is 0.5, and a large effect size is 0.8. So for, remember this is dividing by the standard deviation. So this is sort of for every bit of difference in mean, how much variance are you accounting for? Okay. And then finally, I'm not going to talk too much detail about confidence intervals, but I do want to mention that the confidence interval, the effect size, just to give you the intuition for this. So an advantage here is that these are maybe easier to interpret in terms of actual decision making. So what does a 95% confidence interval of the effect size mean? Well, it means that if we repeated the experiment 100 times, we expect that that interval would include this particular effect size measured in this experiment 95 out of 100 times. A corollary of this is that if that interval, if the 95% confidence interval includes 0.0, that's equivalent to saying that the result is not statistically significant. That means that 90% of the time that interval would include no effect whatsoever. Okay. And equivalently, if that interval does not include 0.0, then it is statistically significant. Fine. So that's some more terminology here. The other notion we mentioned in talking about publication bias was the idea of a meta-analysis. Okay, so this is looking back over previous studies and combining their results. And so in 1978, Glass sort of statistically aggregated the findings of 375 psychotherapy studies to disprove a claim that psychotherapy was useless. And this was the coining of the term meta-analysis. And this built on earlier ideas from other statisticians, including Fisher, who has this quote, when a number of quite independent tests of significance have been made, it sometimes happens that although few or none can be claimed individually as significant, the aggregate gives the impression the probabilities on the whole would be less likely to have been attained by chance. Okay, so this is individually they look weak, but we can aggregate them to get a more powerful result. Okay, and so the reason I want to bring this up, this idea of meta-analysis, that it becomes even more important in the context of data science because you'll often be working with data that you did not yourself collect. And so thinking of it as a meta-analysis experiment is potentially useful. And then another point is, that big data may have become big because it was combined from multiple different sources. And so understanding when this is okay to do and when this isn't is important. So how do we do this meta-analysis? Well, it's pretty simple. You just want to take a weighted average of the independent studies. Okay. And you want to give, so how do you want to define the weights? Well, you can define it different ways, but you want to give the weight to the more precise studies when possible, the ones that have more power. So a very simple method is just weight by the sample size, right? And so this expression here is the number in your group. So the weight for a group, for a study I, is the number of samples in study I over the sum of all the samples, the total sample size. A more sophisticated way is to use the inverse variance weight, which is 1 over the standard error squared. And I'm not going to give you the formula for standard error. You can look it up. But there's lots of variance here. The main idea is to understand why it's called inverse variance is that if the variance is very, very high on a study, you want to give that lower weight, right? That means it wasn't a very precise study. And this could be because the sample size was low, or it could be for other reasons. Okay, and the standard error is one common method of associating with the variance in this particular case. But again, it's important to understand the intuition rather than just memorizing the formulas. Okay, and then again, as usual, there's a caveat here. This is all for a fixed effect model. It assumes that every individual study is measuring the same true effect. And there's random effects models that help account for the fact when they may not be. And we're not going to talk about random effect models. Okay. So finally, one more term that was brought up in the context of publication bias was, well, sorry, I didn't bring up the term, but one more effect that you saw in the plot was this funnel plot, if you remember. The funnel plot was high variance on one side and it went to lower variance on the other. And so the general term for this that I just wanted to introduce you to is called heteroskedasticity. Okay, and so this is when the variance itself is not constant. All right, so here, as an example, the variance is high. The variance is high over here and low in the middle and high again over here. Now, this is not necessarily a problem. There are ways to correct for this, but it's not necessarily a problem because the estimates that you'll generate are still unbiased. Okay, but it can increase overall error estimates, leading to a reduction in statistical power, right? So you end up with this really high error numbers because all these guys count against you, right? Even though you're actually doing a pretty good job in predictions. So I should say how this plot was generated. This was again simulated data where I intentionally sort of varied the variance along the x-axis. Okay, so chose some x values and then sampled y values according to some distribution that varies in this way. And here I just took the exact same x values but repeated the sampling of the y values many, many, many times. So it gave me this clearer spread. But you can see these solid bars are because the same x values were used across all the experiments. Okay, and the point here is that drawing the regression line over and over again, it didn't change all that much. Okay. All right, we didn't get anything that looked like this, for example. Fine. So again, if the problem here is that you might increase the error and you might lose statistical power because it overlooks a real effect. Okay, so what's a second reason for this decline effect, for the truth wearing off? Well, another one is just people make mistakes, and in some cases there's instances of fraud. And so there's some evidence here that these kinds of things are going up as well. As measured, one way to measure this is by the number of paper retractions, and the number of retractions has gone up fairly significantly, as Norden pointed out in 2011 in an article in Nature. So from the period of time 2001 to 2011, there's been a 10-fold increase in number of paper retractions, but only a 1.44-fold increase in papers themselves. Okay, and so this plot is from two different repositories, PubMed and Web of Science, neither one of which can include computer science papers, by the way. But you can see that it's gone up pretty significantly. Fine. So not going to dive into too much detail into this phenomenon, but I do want to give you one statistical tool that is sometimes used to detect fraud, and that's Binford's Law. Okay. So if you're not familiar with Binford's Law, it's a fun one to be familiar with. So this law predicts the distribution of the first digit of data. Okay. And if you think about it without thinking too deeply, you might intuitively think that this would be fairly uniform. If you have random data, you might see an equal number of 8s and an equal number of 3s, an equal number of 2s, and so on. But it turns out that the distribution is not random in some circumstances, in many circumstances. Well, it's not even, I should say. It is random. It's just not even. The distribution looks more like this. You will get more 1s in the first position than you will 2s, and more 2s than 3s, and so on. And so up to 30% of the numbers you measure are 1s. So this should, blow your mind a little bit. Okay. So some examples of this, before we explain what's going on, taken from, there's a nice website, testingbinfordslaw.com, where they pull real data in and show the plots. This is the number of Twitter users by the number of followers they have. Sorry, not the number of Twitter users. Twitter users by the number of followers they have. Okay. All right, so the list of numbers is just the number of followers. The number of Twitter users whose number of followers begins with the digit 1 is 32.62%, if you can see that. And the red dot is the prediction made by Binford's Law. So not too bad. The number of instances that have the 2 as leading digit is 16.66%, and there's the red dot predicted by Binford's Law, and so on. So not too bad. The distance of stars from Earth in light years follows a similar pattern. This is remarkably close to Binford's Law prediction. Government spending in the UK between the period of time May through September 2010. Again, remarkable prediction. Now, you might imagine there's some selection bias on this particular website, and I can't guarantee that there's not. But, with some reading plus a little bit of trust that I hopefully have built up, I hope to convince you that this is not fully explainable by this website choosing particular data sets for which this is true. Okay. Google books the number of unique 1 grams, and we talked about 1 grams a couple of weeks ago. Terms, essentially, are what 1 grams are. Okay, again, pretty good prediction. So before we give the intuition for this, the intuition is a little bit tricky, but before we attempt to give the intuition for this, you can use it to detect fraud. And so this was an experiment was done by Diekman in 2007 to see if this could be used for detecting scientific fraud. And so what he found was that first and second digits of published statistical estimates were approximately Binford distributed in real studies. Okay, or at the very least, they had kind of a monotonically decreasing distribution. So more 1s than 2s, and more 2s and 3s, and so on, if not exactly Binford's Law. And then what he did was ask subjects to manufacture regression coefficients, basically fitting a line manually, and found that the first digits were actually hard to detect as anomalous, but that the second and third digits deviated from expected distributions. And so this distribution that I gave you in the last few slides, and that I gave you in the actually, I guess I didn't give you the actual formula here. Okay, so the distribution that we'll be discussing is only for the first digit, and the skew in that distribution actually gets suppressed as you go to the second and third digits. But Binford's Law can also be used to express different, yet still measurable distributions of second and third digits. And so there, the second and third digits deviated significantly. And so the conclusion was it is potentially useful as a fraud detection tool in scientific data. And there are instances where Binford's Law has been admissible as evidence in court in cases of fraud, and it's been used by reporters and so forth to argue for evidence of fraud in cases of voting, election, and other kinds of accounting data. on the sort of global scene. Okay, so what's going on here? Well, one way to think about the intuition here is imagine a sequence of cards labeled with a particular number, 1, 2, 3, 4, 5, all the way up to 999,999. Okay, and so put them one by one in a hat in order. And every time you throw a card in, measure the probability that a random selection from the hat would produce a card where the first digit is 1. Sorry, this isn't very well said. It's not drawing the number 1, drawing a card where the first digit is 1. Okay. So what does that probability look like? Well, this figure's a little bit misleading because the x-axis is on the log scale. But if you just look at the heights, what's going on here is on the y-axis is the probability of drawing a particular digit. The blue line is associated with the digit 1. The green line is a digit 2, and so on. And this was generated by a simulation where I really did select random numbers from a distribution. And then I really did order them in the manner described in the previous slide, and put one in and then measure the probability of drawing it, a value with a number 1, or where the first digit is 1. Okay. And so if you think about this, the numbers, what's happened here, this is where 1, and this is 10, and this is 100, and so on. Well, as soon as I put a 1 in, the chance of drawing a card with a 1 in the front is 100%. When I put a 2 in, it's now 50%. When I put a 3 in, it's now 33%, and so on. But then as soon as I get to 10, it goes back up to a higher percentage again. And it stays there, 10, 11, 12, 13, 14, and so on. And then as soon as I get to 20, it drops down a little bit. And so that's why it's climbing here, is through the 10s, and then it starts dropping again, sharply. Okay, and so the point here is that under this model, values where the first digit is 1 always are in the hat already by the time you get to the 2s. And the 2s are always there before you get to the 3s, and the 3s are always there before you get to the 4s, and so on. And so you end up with these peaks are led by the 1s, and the area under this curve, although remember this is a log plot, so the area is not quite right, represents the probability of drawing this. And so the probability does actually get higher. Okay. And there's a few different other models you can find if you read up on this, and I encourage you to. There's other ways to sort of think about the probability here, and there is actually a closed form expression for Binford's law as well. Okay. What are the limitations here? It's not always true, and one of the key situation in which it's applicable is the data set has to span many orders of magnitude. Right? It can't be values between, think about it, if you have values between 50 and 90 and you select those randomly, well, you're not going to get any numbers with the first digit is 1. Okay, and similarly if you do from 1 to 100, well, you have this effect a little bit, but not universally. So you want to span a lot of orders of magnitude. And so this is sort of illustrated by this plot here, is that the red areas represent the probability of selecting something where the first digit is 1, and the blue areas are where the first digit is 8. Okay, and so as long as you span enough orders of magnitude, you get much more area where the first digit is 1. Okay, but if you take a narrow case, well, and then the probability is more defined by the distribution itself, and there's not enough chance for this area under the curve under the digits 1 to get big. Okay. So fine. So I just want to introduce you to that law, mention that it can be used to detect fraud, and then connect the fraud plus chance of mistakes back to this original context we're in of trying to understand the weakness of statistical results, the perceived increasing weakness of statistical results. Okay, so a third potential explanation of this decline effect is exceedingly simple but exceedingly common, and it's maybe the most important one to learn to apply in your own work when you're doing statistical analysis. Okay, and so this is the idea of multiple hypothesis testing. So the problem here is that if you perform experiments over and over and over again, you're bound to find something, right? That's sort of the definition, in fact, right? If you keep rolling dice long enough, you can't just keep rolling dice and then yell Yahtzee, right? You get one shot at it. And the same is true with these experimental design. Okay, and so this is related to the publication bias problem in that you're only showing your positive results, but it's a little bit different because here you're talking about the same sample and you're testing different hypotheses over the same data. And so in these situations, either you shouldn't do it at all, or if you do have to do it for various reasons, you need to adjust the significance level down. That means you need to not settle for 0.05 as the threshold. You need to do something much, much lower. Okay, so to understand why, consider something pretty basic. Over completely random data, and we set the threshold at 0.05, this alpha at 0.05. So the probability of detecting effect where there is none is 0.05. Then the probability of detecting an effect when it exists is 1 minus alpha. Then the probability of detecting an effect when it exists on every experiment you do out of k experiments is 1 minus alpha times 1 minus alpha times 1 minus alpha times 1 minus alpha, assuming that they're independent, right? It's okay to multiply probabilities together if those probabilities are independent. Okay, then the probability of detecting an effect where there is none on at least one experiment is 1 minus that total, right? So first we build up the probability of being perfect, and then 1 minus that is the probability of not being perfect, of making at least one mistake. Okay, so if you plot these numbers, what you get is, on the x-axis here is the number of tests, and the y-axis is the probability of at least one spurious finding, right, making at least one mistake. Well, it goes up like this. So as you get up to sort of 50 hypothesis tests, you're up at the 90% chance of at least one spurious finding. Okay. And so controlling this is known as controlling the family-wise error rate. This is the family-wise error rate of at least one mistake. So this is a pretty stringent. So what do we do about this multiple testing problem? How do we control the family-wise error rate? Well, one solution is the Bonferroni correction, which is just to divide by the number of hypotheses. Okay, so if your significance level is alpha, 0.05, and you do 20 experiments, you're testing 20 hypotheses, you just divide 0.05 by 20. So another correction is the Shiddak correction, which has this extra condition where the tests need to be independent. So even though we talked about in the last slide that in order to make that plot, we were assuming that they were independent, but the Bonferroni correction in general does not need to assume that. Okay, so if you're doing hypothesis tests that are related to each other, you can still do the Bonferroni correction. However, to derive this Shiddak correction, we're going to rely on the fact that we're going to multiply the probabilities together. Whenever you see probabilities being multiplied together, that means that you're assuming that they're independent. Okay, so let's see if we can build this up. So here we're going to derive the individual test, the corrected significance level, from the overall significance level. So we're going to set the overall significance level, alpha, equal to the probability that at least one of the tests is significant. All right. So at least one is significant. Well, what's that? That's 1 minus the probability that none of them are significant. And the probability that none of them are significant, assuming independence, is the probability that the first one is not significant times the probability the second one is not significant, and so on. So that's 1 minus alpha c raised to the k experiments. Right? 1 minus alpha c times 1 minus alpha c times 1 minus alpha c, and so on. And that's what this expression says. So fine. So now we just solve for alpha c, and we get this expression, 1 minus alpha raised to the 1 over k, raised to the k root. The kth root of 1 minus alpha. Okay. Okay, so showing the same plot from before, but now zooming the scale in down around 0.05 where the original significance level was, you can see the difference between these two corrections. So the Shaddack correction is more conservative than the Bonferroni one correction. So Bonferroni evens it out across. So instead of increasing the likelihood of making a mistake quickly, which is what the previous plot shows, this is zooming in at 0.05 and showing that the Bonferroni makes it constant across regardless of how many tests, which makes sense because you're just dividing it by the number of tests you've done. Okay. And the Shaddack correction is even more conservative. All right. So that's what to remember. Both of these are considered to be more conservative than is perhaps necessary. You give up too much statistical power when you use these. And in fact, any correction for it goes back to the actual definition of family-wise error rate is considered to be too conservative. So another way of controlling for multiple hypothesis tests that is less conservative is by considering the false discovery rate. Okay. And so the false discovery rate you can understand by going back to our grid and labeling it a slightly different way. Okay. So here, the mnemonic here is that the total, let's see, T and F stand for true and false, and D and N stand for discovery, non-discovery. So false discovery is FD, true discovery is TD, true non-discovery is TN, and false non-discovery is FN. Okay. With this notation, the false discovery rate, FDR, which is sometimes called Q, is the number of false discoveries over the total number of discoveries. And so here in this notation, by the way, D is equal to FD plus TD. So these are counts. These are the number of true relationships and false relationships and so on. Okay. So this is the rate you're trying to control for. So the Bonferroni correction and other family-wise error rate corrections tend to wipe out evidence of the most interesting effects. We say they suffer from low power. So the false discovery rate controls offer a way to increase power while maintaining still some principle bound on error. Okay, and so it's more intuitively it's based on the assessment that 4 false discoveries out of 10. If you reject the null hypothesis 10 times, you make 5 quote discoveries. Having 4 of those be false is really bad, but it's much worse than making 20 false discoveries out of 100. The idea here is that finding true effects is a good thing, and so even though you're going to make some mistakes, if you can, the more you find, the more sort of value you've added. So how can you control the false discovery rate? Well, the Benjamini-Hochberg procedure gives you a way to do this, and so here's how it works. You compute the p-value of your hypotheses, and then you sort them in ascending order, such that the ones with the lowest p-value, which are the most likely hypotheses, right, the ones that are best supported by the evidence, come first. Okay, and then you apply this condition where the p-value is subject to a more stringent condition than just alpha. Remember, alpha is your 0.05, your cutoff, and what we're trying to do is correct for the multiple hypothesis testing, so we want a much more stringent alpha. And so that more stringent alpha is this ratio I over M. And so I is just the rank order of the hypothesis you're testing. And M is your total number of hypotheses that you're testing. Number of hypotheses. All right. And the procedure says, well, find the highest I for which this condition holds, and then reject the null hypotheses for all I lower than that, except everything up until that point. Okay. And so here's what it might look like with 50. The first, and 0.05, I suppose I should have put that. So your first hypothesis has to, the first hypothesis is compared with a pretty stringent condition, 1 in 1,000. and the second one is double that, and the third one is triple that, and so on, all the way up to the 50th one, which would be 50 over 50, which is just your original alpha, 0.05. Okay, so this is a much tighter condition. And so what they're able to prove is that under these conditions, following this procedure, the false discovery rate is less than T over M times alpha, where if you remember, T was the total number of cases where the null hypothesis is true. Okay. So here's what it looks like graphically. The little x's are above this line, and the dots are below this line, and the x-axis is rank order, and these are all your 50 hypotheses sorted in increasing p-value. And the line represents that threshold condition, and it slopes up with rank order, as we'd expect. And so here we'd say we'd find the highest I for which this condition holds, and accept everything lower than this. And here we had a pretty good run. We accepted sort of 30 out of 50 hypotheses. And notice that these actually are above the line, but we would still accept them. Okay. Okay, so where are we now? So we motivated the discussion of statistical inference and estimation by bringing up this so-called decline effect, where the effect size of scientific results seems to be going down over time, and reproducibility is suffering. And so we gave some reasons for this: publication bias, mistakes and fraud, and this multiple hypothesis testing problem. And so we used these motivations, these scenarios, to bring up various topics and techniques. So we talked a little bit about basic statistical inference, where I just gave you an overview, and that's it. We talked about effect size. We brought up the specific term heteroscedasticity. For fraud detection, we brought up Binford's law. And then with multiple hypothesis testing, which is perhaps the most important part of the discussion, we talked about the family-wise error rate and the false discovery rate, and gave correction procedures for both of these. Okay, and so this hopefully was a tour of not just some basic concepts, but also some, if not advanced, at least things that don't necessarily come up in a Stats 101 course. But I think it's pretty important for a data scientist to understand. In fact, as a data scientist, there's a view among statisticians that these topics are not very well understood. And in fact, they'll point to typical machine learning classes where understanding the population, understanding the various biases, understanding how to correct for the problems that can arise is not taught at all, and it's more of a blind application of algorithms. And so I think it's pretty important to sort of go over this choice of topics. Now, so what about big data? What changes? Well, so Brad Efron, who's a world-renowned statistician, describes it this way. It says classical statistics was fashioned for small problems, a few hundred data points at most, and just a few parameters. And the bottom line is that we've entered an era of massive scientific data collection with a demand for answers to large-scale inference problems that lie beyond the scope of classical statistics. And so suggests that something is changing in the era of big data. Now, what can go wrong here? Well, as we talked about, you can find spurious relationships in big data. And so this is a picture that I got from a colleague recently that was emailed to him, which is a plot that someone took the time to make. May or may not have been as a joke, but as you can see here, it says Internet Explorer versus the murder rate. Okay. And so this is the murders in the US in blue, along with the market share of Internet Explorer in the green, and the corresponding discussion that went along with this plot was somewhat amusing, right? Talking about various theories for why the murder rate might be going up as Internet Explorer market share, or murder rate goes down as Internet Explorer market share also goes down. But the point here is that without some common sense, or without the application of understanding the scenario of the problem, you can make discoveries of this form. Okay. All right, and so other examples that have been talked about in the literature, again, brought up as bad examples, the number of police officers and the number of crimes. So why might these two things be correlated? Maybe police officers cause crimes. Well, no, probably because there's in densely populated areas there are both more police officers and there are more crimes. By the way, just to point out again, these authors here are not authors that made these claims. These are authors that brought up the mistake. Okay, amount of ice cream sold and deaths by drownings. Why would these things be correlated? Well, there's a seasonality, right? In the summertime, you sell more ice cream and more people go swimming. And then one is, stork sightings and population increase used as, evidence that storks do indeed bring newborns to families. Well, again, in more densely populated areas, there's more people to actually see the storks, and so you get an increase in sightings. Okay, so these kind of procedures to remove bias and these procedures to understand the population you're sampling from and to understand the possibility of spurious correlations, these things are taught in statistics programs but are not typically taught in machine learning classes. Okay, so what does it have to do with big data? Well, it might be a view that there's the curse of big data, as Vincent Granville put it, is the fact that when you search for patterns in very, very large data sets with billions or trillions of data points and thousands of metrics, you are bound to identify coincidences that have no predictive power. And so the example he gives is to consider stock prices for some large number of companies over a 1 month period, and then you check for correlations in all pairs. And actually it doesn't stop there, because that would be over the exact same 1 month period, but you might want to account for lags. Perhaps the stock price of Google a few days later affects the stock price of smaller companies that depend on Google. Okay, and so now you're not just comparing every 500 squared. You're not just checking the pairwise correlation of these time series, but you're also checking the pairwise correlation among the slightly offset one. Okay, and so these are this cross correlation procedures. So very basic time series analysis is just to measure the correlation, and I just wanted to throw the formulas up here, where the covariance of two data sets is measured this way. All right, so you take the data point xi and subtract the mean of x and multiply that by yi minus the mean of y and add all that up, and that's the covariance. And then you divide the covariance by the standard deviation of each data set multiplied by each other, and so this gives you a correlation. Okay, so what does this experiment look like? Well, I generated this plot by running random walks for stock prices that start at $10. They all start at the same point, and at each step, which is an hour of simulated time, draw a sample from a normal distribution where the mean is the current stock price and the standard deviation is 1% of that current stock price. Okay, and this is not especially defensible, but you can see just sort of visually that it does generate stock price looking things, and you do get some variance here. All right, so clearly this is random. This plot shows the number of correlations at a level of 0.9. All right, that's a pretty strong correlation as a function of the number of stock prices tracked. So as I went up from 10 to 100, I didn't go all the way up to 500, which is what Vincent Granville described in the thought experiment. This is the number of spurious correlations you find. Okay, and this is also not doing the lagged cross correlation, right? This is just directly computing the correlation of these two time series across this month, and that's a pretty long period too, across a month. So what's the point? Well, big data gives more opportunities for spurious findings. Okay. Now, it's not all bad news. So how is big data different? Well, there's a notion of big P versus big N, where big P is sort of the number of columns and big N is the number of rows. And in this experiment we just did with the time series, this was sort of a big P scenario. We looked at more, an increasing number of companies, and then we looked at all possible correlations between them, so this was growing sort of quadratically. Okay. So the thing about big data, though, is that the marginal cost of increasing the number of records is essentially zero. It's gotten cheaper and cheaper and cheaper to collect data. Okay. Great. Now, that's very, very powerful, right? We want to increase the number of records, add statistical power, and helps us sort of, get lower and lower p-values. But it also amplifies bias. If you're collecting the wrong data, if you're looking at the wrong populations, you're going to make, so-called discoveries that are simply false. And so, for example, if you log all the clicks to your website, you have a very, very large data set, and you can very precisely model user behavior. But that would only model your current users when your whole, perhaps the whole point of modeling user behavior is to try to attract new customers. Well, for example, if you have early adopters and your current user base is early adopters, you're only going to be modeling their behavior. You haven't actually sampled the population at large. Another example is mobile data, and this comes up in polling for, say, the presidential election. You're only sampling people that have cell phones. And this may or may not be the same population you want to be sampling. Okay, so this may ignore lower income groups or different age groups. Okay, you need to be careful about multiple hypothesis tests as well, as we pointed out. So there's a fantastic comic from XKCD that makes this point very, very clear, where they sort of demonstrate that green jelly beans cause acne, right? And the story here is that there's 20 different colors of jelly beans, and for a p-value of 0.05 we do 20 experiments, and sure enough we find one of the colors indeed causes acne, but that would be expected purely by chance. And so I encourage you to look up that comic. And then the other comment I'll make that we will probably come back to is Nassim Taleb's black swan events. So this is things that are sort of inherently unpredictable, or the distribution of them does not follow a normal distribution, sort of a bell curve distribution, where the tails of the bell curve mean that extreme values become exponentially more rare. That's the sort of definition of the normal distribution. But in some cases, extreme values are not exponentially less common. They happen. Okay. And so the example that he uses in this case is that, if a turkey was to model your behavior, it would get increasingly more confident that that you mean it no harm, and you mean it goodwill, right? Every day you come and feed the turkey, and every day you take care of it, and you look out for its well-being. But then on the day before Thanksgiving, it gets slaughtered, perhaps. Okay, and so that was Taleb's argument for black swan event. And black swan itself refers to the fact that people didn't believe black swans existed, and then finds out that they did, and so it was an unexpected event. Okay, fine, and we'll talk more about that in some detail. Okay, so far we've been discussing statistical inference from a particular perspective, which is the frequentist perspective. And so frequentists are concerned with the probability of seeing a particular data sample given the null hypothesis. Okay, and that's what the p-value gives you. But there's another perspective to statistics called the Bayesian approach, which is concerned with the probability of having a certain outcome given the data that we've already seen. Okay, and so I want to talk a little bit about Bayesian approaches and give an example of their power. Okay. What are the differences here? Well, you can think about the differences in terms of what is fixed. So the frequentist perspective is that data are a repeatable random sample, right? You're always allowed to go do another experiment the same way. And in fact, you need to, at least virtually, to reason about the probabilities that get produced by these methods. Okay, so there is some sort of frequency you can reason about, frequency of achieving a certain outcome. Okay, and the underlying parameters of the population remain constant during this repeatable process, right? The population stays fixed, and you run experiments to determine likelihoods. Okay. Meanwhile, with the Bayesian approach, the data are observed from a realized sample, and the parameters of the population are unknown but can be described probabilistically, right? So they're not sort of fixed values. However, the data are fixed, right? You don't think about going back and sampling more data. You just have the observations you have. Okay. And so the Bayesian approach is 100% concerned with the application of Bayes' rule, which is this. Okay. And so what Thomas Bayes did was relate these conditional probabilities with the prior beliefs. Okay, so it allows you to take your belief about the probabilities of certain events happening and update them when more data is collected. Okay, and so here's what it says. It says the probability of event A happening, given that event B has already happened, is equal to the probability of B happening, given that A has already happened, multiplied by the probability of A happening across the board, divided by the probability of B happening across the board. And if that's not clear, that's okay. We're going to go into more detail here. So for right now, though, recognize that the key benefit here is the ability to incorporate prior knowledge, which is not the case with the frequentist approach. Now, a key weakness here is that you need to incorporate prior knowledge. So there's a couple of problems with this. One is if you don't know anything about the population you're modeling, then there's not much you can do with the prior. There's not a good way to model this the distributions. Now there are some techniques to sort of derive so-called uninformative priors that try not to influence things too much, but give you a plug-in to be able to apply the rule. But still, that is an issue. Fine. Perhaps more insidiously, and the reason why Bayes' the Bayesian approach was popular and then fell out of favor in the earlier part of the 20th century was that you can use this rule to kind of do anything you want, to confirm or deny the effect of any sort of evidence, right? Just by plugging in your own prior beliefs. Okay, so given a fixed set of data, two different people could come up with different conclusions about the data because they had different prior beliefs. They modeled the prior distributions differently. Okay, and this was seen as a major flaw and gave rise to the frequentist approach, which looks more or less objectively at the data itself. Okay. Right, and so that's what is spelled out here in a nice essay by Matthews, 1998, is that different people could use Bayes' theorem and get different results. And so faced with some experimental evidence for, say, ESP, true believers could use Bayes' theorem to show that the new results confirmed it, while skeptics could use it to show that the ESP didn't exist. Okay, and both views are possible because Bayes' theorem only shows how to alter one's prior level of belief, and different people can start out with different opinions. Okay, so that's the issue. However, the frequency-oriented, the frequentist approach. So the frequentist approach, laid out by Fisher and others, were able to achieve what was thought to be impossible, which is a way of judging the significance of experimental data independent of any prior beliefs. Okay, so he had found a way that anyone could use to show that a result was too impressive, was too statistically significant to be dismissed as a fluke. And all you had to do was convert your raw data into this thing called a p-value. All right. Now, you still have to have some sort of a threshold to measure the significance of this p-value, and that was written up as 0.05 by Fisher, in a original paper. So what were the insights that led to this particular value of 0.05? Well, Fisher admitted that there weren't any. He simply decided 0.05 because it was mathematically convenient. Okay. And many people have pointed out, say from the 60s on, there's been periods of time where there's been a significant amount of work showing that this approach with these particular thresholds are able to produce a lot of incorrect conclusions. So James Berger at Purdue wrote an entire series of papers warning about the, quote, astonishing tendency of Fisher's p-values to exaggerate significance. Findings that met the 1 in 20 standard can actually arise when the data provide very little or no evidence in favor of an effect. Okay, so that's the problem. So now, perhaps we can say that the pendulum is in some sense swinging back towards the Bayesian approach. One more problem with the Bayesian approach that I'll bring up that I don't necessarily have a slide on is that, which we'll see in a little bit of detail in perhaps the next segment, is that these conditional probabilities and these prior probabilities end up forcing you to model a situation mathematically, and that situation may be very difficult to model mathematically. Okay, so what you do is you get these. What you end up with is these chains of complicated conditional probabilities that need to be integrated in order to apply Bayes' rule. And so this was computationally intractable, and there was a huge number of tricks and simplifications and ideas used to make this more tractable. Okay, but thanks to the development of methods that allow you to sample these complicated distributions computationally, this approach is becoming increasingly popular. Okay, and there's a lot of thinkers in this space that believe that, for the 21st century, a combination of frequentist and Bayesian approaches is going to be dominant. Okay, so for these reasons, we're going to make sure we talk about the Bayesian approach at a very introductory level and leading up to a machine learning algorithm called naive Bayes. All right, so we talked about Bayesian versus frequentist approaches to statistics, and this cartoon is my attempt at a quick summary. So the frequentist approach is concerned with using the data and only the data to make a decision, while the Bayesian approach incorporates prior belief as well as the data. Okay, and that's both a strength and a weakness. Strength in that if you have good information, you can incorporate it. If the weakness in that you have to actually incorporate information and that it's somewhat subjective, depending on who you're talking to. Fine. So Bayes' theorem, breaking it down in a little more detail, you've got this terminology you can apply to it. So the prior, as we said here in blue, is the probability of the hypothesis being true before you've collected any data, right? So what's in the global population, how many people are above a certain height? Okay. Then the marginal probability is what is the probability of collecting this data, this particular data observations under all possible hypotheses? Okay. And then the likelihood is the probability of collecting this data given that our hypothesis is actually true. And then finally the posterior is what we're usually trying to compute, which is the probability of our hypothesis being true given the data collected. Okay. So let's think about it this way. Arrange this into a grid. This is it's actually pretty trivial to derive this theorem if you think carefully about what's going on. So a nice way to explain it is to build a 2x2 grid like this, where you have A and B, and not A and not B. And the box here is the probability of A and B happening. Okay. Well, A and B is the probability of A given that B has already occurred multiplied by the probability that B occurs. Right? And you should take a moment and convince yourself of that. Equivalently, it's the probability that of B occurring given that A has already occurred multiplied by the probability that A actually occurs. Okay. So these things are all equivalent. Set these two things equal to each other and just divide. So set these two things equal to each other and divide both sides by probability of B occurring, and you have Bayes' rule. All right, so let's try this out. So here's a question. Say you know that 1% of women at age 40 who participate in routine screening have breast cancer. And let's say you know that 80% of women who actually do have breast cancer will get a positive result from the test. Further, say you know that 9.6% of women who do not have breast cancer will also get positive results. So this is the false positive rate. Okay. Now, given that you know that a woman in this age group had a positive test, right? The test came back positive in a routine screening. What is the probability that she actually has breast cancer? And you should take a minute to sort of work this out. All right. So what's sort of remarkable is that this is a fairly straightforward application of Bayes' rule, but intuitively it's easy to make sort of mistakes. in the reasoning. And in fact, when you ask this, there's been some famous studies that are now somewhat out of date where they asked doctors this question, and the doctors came up with wildly wrong answers. Only 15% of the doctors they asked were able to answer the question correctly. Okay. So here's how to break it down. Again, with our 2x2 grid, we've got 1% of cases that have cancer, and we've got 99, which means we have 99% of cases that do not have cancer. This is in the global population, right? And let's say we just know this, right? We know that 1% of people all across the board have cancer, or at least in this group that we're studying. I shouldn't say across the board. Okay. Now, we also know that if you have cancer, there's an 80% chance that when you take the test, it'll come back positive. Okay. So the true positive rate is 1% have cancer times 80%. Now, we're also given that if you do not have cancer and you take the test, you'll get a positive result at a rate of 9.6%. And so the false positive rate is the rate of not having cancer, 99%, times 9.6%. Now, similarly for the false negative and true negative tests, 1% times 20 times 1 minus 80, and 99% times 1 minus 9.6 is 90.4. Okay, so we have all the information we need. So going back to actually answering the question, we can write down Bayes' rule. So what is the probability of having cancer given that we have a positive test result? Well, that's the probability of getting a positive test result given that we have cancer, multiplied by the probability of having cancer overall, divided by the probability of a positive test overall. Okay. So the only one of these terms, so we actually know this term straight out. We're given this one, right, which is 80%. And we're given this one. The probability of cancer overall is 1%. We don't have this denominator given, so we need to figure that out. Well, that's the chance of a positive test in all other occurrences. The chance of a positive test given that we have cancer and the chance of a positive test given that they don't have cancer. In each case multiplied by the probability of that happening. Okay, so you can decompose this. So that's 0.8 times the 1% probability of actually having cancer plus 9.6% times 99%, which gives you this number of 10.3%. So that's the overall probability of getting a positive test result. All right. And so now you plug this in and you end up with a number of 7.8% for our answer. If we have a positive test result, the chance of actually having cancer is 7.8%. So this is lower than you might come up with if you don't think about it carefully, right? You might think that, boy, I got a positive test result. There's this 80% number floating around. You know, boy, there's probably a 70-80% chance that I have cancer. But because of the very low percentage of having cancer in the prior probabilities, the actual number is still pretty low. Okay, so it's easy to make mistakes with this stuff. Now, this was a remarkably simple case. First of all, we're given all this information. Second of all, there's only two possibilities. There's these sort of binary variables. So let's think about something a little more complicated. Okay, so let's consider a classic application of Bayes' rule to a big data problem, which is spam filtering. Okay, so here our task is to determine whether an email message is spam, the probability that an email message is spam, given the words in the email message. Okay. And with Bayes' rule, you can express that probability as the probability that the email message is spam overall, multiplied by the probability of seeing these particular words in the message, given that we already know it's spam, and all that divided by the probability of seeing these words in the message. Now, the interesting one here is this numerator. And the reason is that the probability of words appearing doesn't involve the unknown label of whether it's spam or not. And so all we're trying to do is get a relative frequency of spam or not spam. Okay, and so just dividing by a constant factor of the probability of seeing these words doesn't actually change our decision at all. So we don't actually care about the actual number, we just care about the decision of spam or not spam. Okay, So fine. So re-expressing this, before we get rid of the denominator, re-expressing this, what do we mean by words? Well, you can rewrite this as probability that the email message is spam, given that the word Viagra appears in the message, given that the word rich appears in the message, given that the word something more innocuous, perhaps like friend, appears in the message. So all the words, in the English language, or all the words of interest to us in this test. Okay. So that's re-expressed that way. Now, this numerator can be rewritten in the following way. Given that it's a conditional probability, we can apply a chain rule, a repeated application of the definition of conditional probability to obtain this. The probability that it's spam multiplied by, so let's see, so this expression rather can be expressed as the probability of seeing the word Viagra, given that it's spam, multiplied by the probability of seeing all these other words, given that it's spam and given that it's Viagra, or given that the email message contains Viagra. And then you can keep going. This probability times the probability of seeing the word rich, given that it's spam, and given that it's Viagra, multiplied by the probability of all the other words, given that it is spam, given that it contains the word Viagra, given that it contains the word rich, and so on. Okay. So this is a long, complicated, conditional probability, and this is where the naive Bayes assumption comes in. So under the naive Bayes assumption, we say that the probabilities of these different words appearing in the email message are completely independent. That it's no more likely for you to see the word rich when you see the word wealth than it is, without the word wealth there. Okay, this isn't true, right? Obviously, words go together. There are co-occurrence rates, right? But you just ignore that and just treat everything as completely independent, which allows you to simplify this expression as just a sequence of probabilities. What is the probability of seeing the word Viagra given that it's spam? What is the probability of seeing the word rich given that it's spam, and so on? Now, how do you get these probabilities? Well, you have data, right? You have a set of documents that have been pre-labeled as spam, and you can look at the number of them that contain the word rich and divide by the total number. Okay. And so now you can calculate the probability of the two classes, spam and not spam, and apply a decision procedure to call it. And in fact, a simple one is just whichever one is more likely, whichever one has the higher probability. It's called the MAP decision rule, which stands for the maximum a posteriori.